KNN is one of the easiest machine learning algorithm to learn and understand. Instead of building a complex mathematical model, it simply looks at the nearest points and let them decide the prediction. How does Netflix recommend movies? How does an online store suggest products that you might like? Many recommendation systems today rely on the idea that similar things are usually found close together. That is the core idea behind K-nearest neighbor. We will explore the complete KNN workflow with practical examples. So KNN is a machine learning algorithm that is primarily used for classification, but it can be extended to regression as well. It is a kind of supervised learning, and it is also called as lazy learner algorithm because though it is a machine learning algorithm, it does not learn from the machine learning data set. Instead, it will store the entire data set, and whenever it has to do the classification on any of the unknown sample, it will run the computation each and every time. So that is why it is called as the lazy learner algorithm. This point is very important, so please pay attention. Now let us try to understand what are the different steps that are involved in order to perform the KNN algorithm. It all starts with the data preparation. We will use the scikit-learn datasets to run the KNN algorithm. So at that time, we can talk about data preparation in detail. Once the data preparation is completed, I move to the next part, which is choosing the value of k. As an example, consider that if I'm joining a new school and if I want to understand which club I should be part of, what I can do is I can look at some of the students that are very close to me and then try to understand what club they are part of. And if I'm deciding that I am looking at 5 students, so the value of k is going to be 5. If I only want to see 3 people that are very closer to me, the value of k will be 3, right? So this way I can choose the value of k. Basically, it is the number of neighbors that I have to consider. Once I choose the value of k, I move to the next part, which is calculating the distance between the new points and all the points in the training data. So in the data set, we will have a unknown sample, and the distance between this unknown sample to all the other points in the data set will be calculated. Now, when we talk about distance, primarily we use the Euclidean distance, which is the most common distance. But apart from this, there can be other distances as well that we can consider. Once we calculate the distance, we move to the next part, which is find the k closest points. So if in the step number 2, I identified that k is going to be 3, I find the k closest points, or basically from the Euclidean distance, the 3 shortest distances. And once I know the 3 shortest distances, if out of these 3 students, if student 1 is part of basketball club, student 2 is part of football club, and student 3 is again part of basketball club, then I will consider basketball club as the classification, and I will say that I'm going to join the basketball club. So this is what my step 5 is. So these are some of the steps that we have to perform whenever we have to run the KNN algorithm. Now let us try to visualize the KNN with some example. Let us suppose this is the unknown sample and there are some class that already exists. I have class 1 that is in blue. I have class 2 that is in green. And I have class 3 that is in red. Now I want to consider and understand what is going to be the class for the unlabeled point. This is the unlabeled point. Now, how do I understand this? In order to understand this, I am going to calculate the distance of this point from each of the point in the data set. So for example, I will have to calculate the distance of this x from each of these points. Similarly, I will need to take the distance from each of these points. And similarly, I'll calculate the distance from each of these points. So after calculating the distances, I understand that these 3 points are very close to me, right? So because I have k equal to 3, so I will be looking at these 3 points. Now, if you take a look at these 3 points, you can see that out of these 3 points, two are red and one is blue. So majority wins, and I can classify that this label belongs to class 3. This is how we perform the KNN example. Now let us perform the same exercise one more time, but this time let us consider the value of k to be 5. So in this case, I need to calculate the distance of this point from all of these data sets. And then finally, I have to find the 5 points that are very close to me. So after understanding the distance of this x from each of these points, I may be able to understand that these 5 points are lying very close to me. What are these 5 points? I can have this 1, 2, 3, 4, and 5. So I can see that there is one blue, two red, and two green. So this has to be a tie between green and red. But if I see the distance, the red ones are more close to me. So obviously I can say that this point, the unlabeled sample, belongs to class 3. This is how we run the KNN algorithm. Now let's talk about some of the distances that we have to use whenever we have to run the KNN algorithm. The first one is the Euclidean distance, which is very common. And this is basically the shortest distance between any 2 points. So if there are 2 points, x1, y1 and x2, y2, the shortest distance between them would be the under root of x2 minus x1 whole square plus y2 minus y1 whole square. This is the basic distance that we use in the coordinate geometry, and this is typically the shortest distance. So this distance is also used in KNN algorithm. There is one more distance that we typically use in KNN algorithm, which is called as the Manhattan distance. Why it is called as the Manhattan distance is because it is inspired from the map of Manhattan. If you see the map of Manhattan that is based out of the New York, you will be able to find that we have the layouts in this form of rectangle or the square. So whenever we have to move between point A to point B, typically you can take four directions. You can either move left, or you can move right, or you can move up, or you can move down. So the same thing applies to the Manhattan distance as well. If I have point A and point B, and if I have to move between the point A to point B in Manhattan distance, this distance is given by the summation of modulus of x2 minus x1 plus y2 minus y1. So we have to take the modulus of x2 minus x1. We have to take the modulus of y2 minus y1 and then add these two numbers to get the Manhattan distance. So for example, if the coordinate of A is 2, 3 and B is 6, 7, what we have to do is we have to take the modulus of 6 minus 2, which is 4, and also the modulus of 7 minus 3, which is 4, and we have to add these two numbers. So the Manhattan distance will come to 8. Basically, what it signifies is if I have to move from point A to point B using the Manhattan distance, I will go 4 unit this side and 4 unit this side, and a total of 8 units is my Manhattan distance. Now you may wonder, how do we choose the right value of k? So there is no set standard on how we decide the value of k. It is primarily hit and trial. There are some methods as well. So for example, if there are n number of samples in a data set, we can take the square root, and the closest number to that square root can be my k. One more thing to note here is we have to avoid the even numbers. Why we have to avoid the even numbers is because if I take k equal to 2 and if the distance of a point, the unlabeled point, is equidistant from these two samples, then in that case it is very hard for me to classify this unlabeled sample. Instead, when I take k equal to 3, even if 2 points are equidistant, I can take a look at the third point and then decide the classification of the unlabeled sample. Also, we have to be mindful that k should not be very large or very low. We have to find a middle ground in order to understand the right value of k. What happens is, if the data set is typically very large, using a larger k would make sense. But when you use a larger value of k, the model may become very simple and it may go underfit. On the other side, if the value of k is very small, it will result in overfitting. Now let us try to understand the concept of underfitting and overfitting. Let's take an example. We have two set of students and their exams are coming up, and they started using the sample papers or the mock papers. Now there are one set of students. There are one set of students, so set one, and or maybe I should call it as a group. So I will say group A and I have group B. So these two set of students are there. Group A set of students, what they do is they will take the mock test very seriously. They will try to memorize everything. They will try to memorize everything. Even if there is any error in the mock exam, they will try to again memorize it. So what happens is they perform very well on the sample test, right? They will get very good marks when they attempt the sample test because they have memorized everything. But when the real test comes, they will not perform good because they have not paid attention. They have just memorized the questions. It is not like the same data they will get or the same. It is not that the same questions they will also get in the real exam. Real exam will have real questions, and again, they may not be able to perform very well. So this is the case of overfitting, when the model performs very well on the training data, but it does not perform well on the testing data. Similarly, there is another group of students. They are not taking the mock test very seriously. Obviously, if they are not learning from the mock test, they are going to perform very bad on the training data, meaning they will perform very poor on the mock exams, as well as they will perform very poor on the test data. That is, they will perform very poor on the real exam as well. So this is how we define the underfitting and overfitting. So when we talk about overfitting, typically it is very complex model. Number of features is very high. So number of features would mean that the number of type of questions, right? So different type of questions. For example, we can have fill in the blank. We have the MCQs. We have the objective questions. We have the subjective questions. We have the match the columns. There are different type of features. There are different type of questions that the student will be exposed to, that the model will be exposed to. So the student will perform well in the sample test, but they will not perform well on the real exam or the real test. Similarly, the model that is overfitted will perform well on the training data set, but it will not perform well on the testing data set. And when I come to underfitting, here we have less complex model. There are low number of features. So the students are exposed to only few questions, right? They will just learn two questions and they are expecting these two questions to turn up in the main exam, which is not the case, right? So the students will fail badly on the sample test as well as on the real test. Similarly, the model will not perform well on the training data set as well as it will not perform well on the testing data set. When we try to visualize the concept of overfitting and underfitting in a graph, this is how it looks like. So let us suppose we have two features, x1 and x2. So in all the three cases, you can see that there are these two features, x1 and x2. Now, there is a function. So anytime when I talk about machine learning, y is equal to f of x. So this y, that is basically my target or my output, is a function of x. It can be any kind of function. It can be a linear function, it can be a polynomial, it can be any sort of function, right? But the thing is, it depends on x and it is a function of x. So you can see that when we try to overfit the model, basically what happens is the model tries to cover each and every data set and it forms a curved line, right? So for example, the student, they will try to memorize each and every question in the mock exam, right? So they will try to touch upon each and every question. So this is what the model is also doing, okay? And it will result in overfitting. When I talk about underfitting, it basically means that the student, they have only two questions and they will just look at these two questions and linearly it will perform, right? They will not take a look at these questions that are available in the mock test or the mock exam, right? So this is the case of underfitting. And in between overfitting and underfitting, we have to find a best fit that is called as the optimum fit, right? So there has to be a middle way where the model is not overfitted, where the model is not underfitted, and it provides the correct classification. Obviously, it comes from trial and error. Now let's try to understand the curse of dimensionality. It basically means that the KNN algorithm works well in two dimension. When I say two dimension, it is x1 and x2. So x1 and x2 basically are our features. So when you have only two features, the KNN will perform very well. But as and when you keep on increasing the number of features from x1, x2 to x1, x2, x3, that is the 3D plane, or the 4-dimension plane, or the 5-dimension plane, or the n-dimension plane, that is also called as the hyperplane, the model will struggle. The KNN model will struggle. And why it happens is, let's take an example. We have to classify a person on the basis of two features, age and city. So we have a data set of 100 people where we have for these 100 people their age and their city. And if I want to classify one person, I can take a look at these 100 samples and also try to classify this unknown person based on the two features, that is the age and the city. That is something that is doable. But let us suppose if I have more than two features. So instead of age and city, in addition to these two, I also have salary. I also have the data about their height, their marital status, their education background, their favorite color, and maybe there can be 50 other features as well. Now, it is very difficult to find the similarity from the 100 people of an unknown people based on these features, right? Because there will be the data set. If you plot this data set, the points will be very far, right? It will be all scattered. So finding the similarity based on the features, when you have multiple features, when I say the multiple features, it is typically the n number of features, right? More number of features. So it is very difficult. And the KNN will struggle in this case because it relies on distance. And when I talk about the hyperplane, all the point becomes apart from each other, right? So if you talk about two dimension, all the points will be closer to each other. So it is easy to understand that, okay, this point is very close, this point is very far. Let me classify this unknown data as the class of this point, right? But the same thing we may not be able to do in case of hyperplane because the points are very distant. So there is no nearest neighbor as such, right? All the neighbors are very far from each other. So there is no concept of nearest neighbor, right? Because there are no 2 points in a hyperplane that lies very close to each other. So there is no concept of n nearest neighbor in case of a hyperplane. So that is what the curse of dimensionality is. So that is it for today. We will continue our discussion in the next video. where we will take a data set from scikit-learn and try to perform the KNN exercise. Please consider subscribing and give a thumbs up. And thanks for watching.